All right, now let's look at the third FRQ question in the set. The third problem in the International Practice Exam 2019 involves this setup of three blocks connected to a series of strings and pulleys and sort of a modified, more complicated version of an Atwood machine. All right, so we're told a few things here. For one, there's no friction between block B and the table. We're told that the pulleys can be considered massless, so you don't have to consider the rotational inertia of these pulleys. And we're also told that the system is at rest initially. All right, so part A of this problem has two parts. We're asked to construct a free body diagram for blocks A and B. So starting with block A, if this dot represents block A, there's going to be a gravitational force in the downward direction. That will be ma times g. There will be a normal force from the surface of contact between blocks A and B. So that's going to push upward. I'm going to call this force F sub AB, just to distinguish that from the normal force that block B feels from the table later on. All right, so in the horizontal direction, string 1 is under tension and it's going to be pulling block A to the left. So let's call this force T1. And then there is static friction between blocks A and B. In this case, since the system is at rest, there needs to be a zero net force, so the static friction must point in this direction, and it should be equal in magnitude to the tension. All right, so this is block A. All of these forces cancel out, so the object is in equilibrium, so it remains at rest. In part 2, we're asked to do the same thing for block B. There are going to be more forces present here, so let's just start going through those. So first of all, there will be a gravitational force, just as before. So this is going to be mb times g. There's also going to be a normal force from the table, and that's actually going to be larger than the weight of block B. The reason these two forces are not equal is that there's a third force in the vertical direction. So blocks A and B are in contact, so they are going to push against each other. This will be an action-reaction pair according to Newton's third law, so those forces will be equal and opposite. One of the forces in that action-reaction pair is over here. It's the force of block B pushing up on block A. So block A is going to push down on block B with an equal amount of force. So these two forces here make an action-reaction pair that are equal in magnitude but point in opposite directions. So in the vertical direction, the two downward forces on block B will match the normal force from the table pushing up. All right, and now block B is in contact with both strings. So string 1 is going to pull to the left, and then string 2 is going to pull to the right. All right, and again, you'll notice I did not draw these forces of equal magnitude, and that's because we have another action-reaction pair present here, and that's the friction force between the two blocks. So this friction force here represents block B pushing block A to the right with a certain amount of force. So block A is going to push B to the left with the same force. All right, so we have two forces pulling block B to the left and one force pulling it to the right. All right, so we have a total of 6 forces on block B, and this is what the free body diagram ends up looking like. All right, so now in part B, we want to do a little bit of quantitative analysis here and figure out what is the maximum value for MC, the mass of the hanging block, that will allow the system to remain at rest. All right, so first of all, we need to figure out how the mass of block C factors into these two free body diagrams we've just drawn, and that is through this force here. So if block C is at rest, we could imagine drawing a separate free body diagram for that block. We'll have its weight mcg pulling downward, and then we'll have the tension pulling upward. So this tension force T2, which appears in our free body diagram for block B must equal the weight of block C. So that's one equation we can write to start to work with here. Now if we look at the free body diagram for block B, we know that the tension T2 must equal T1 plus the friction force between blocks A and B. And then if we look at the free body diagram for block A, this friction force must equal T1. So we can combine all three of these equations together and say that the weight of block C must equal T1 plus Fs, but since these two forces are equal to each other, we can just say this is equal to 2 times the friction force. All right, so the maximum mass of block C is going to correspond to the maximum friction force. The maximum friction force between blocks A and B is just going to be the coefficient of friction multiplied by the normal force that those two blocks exert on each other, which we called FAB. And then if you look at the free body diagram for block A, FAB is just equal to the weight of block A. So we finally get this equation here, which sets these two expressions equal to each other. So we just cancel G on both sides and get that the maximum mass of block C is equal to 2 times mu s times the mass of A. All right, now in part C, we're going to look at a different setup here. So now we're just going to get rid of block A and one of the strings and pulleys, make this a little bit simpler. We're just going to put a block of clay or a lump of clay on block B. And then we're going to do an experiment where we will measure the acceleration of the system for different masses of clay. All right, so there's a bit of reading in this section here. It tells you the acceleration of the system is given by mcg divided by mtot, where mtot is the total mass of the clay and the two blocks. All right, so we can write that down somewhere off to the side. Okay, so this says in each trial, a student moves a small amount of clay from block B to block C and then releases the blocks from rest, recording the new values of mass of C, which will include some of the clay in each trial, and the acceleration of the system. And then we're also told that this total mass is equal to exactly 5 kilograms. Okay, so we're given this graph of acceleration versus mass, which I wasn't able to copy down here, unfortunately, but if you look at it on your sheet or your AP Classroom, you should see a scatter plot of some points that look like they form a more or less linear graph. Okay, so first question that we're given here for part C is or we're asked to draw a best fit line to the data points. So I don't think there's really anything I need to show there. You would just put a ruler down over the page and sketch a best fit line. It should be pretty linear. It should go more or less through the origin, have a constant positive slope. So for part 2, we're asked to use this best fit line to calculate an experimental value for the acceleration g. All right, so if we look at the slope of this line, it's going to go through the origin approximately, and also if you look on your graph, the grid lines, 0.5 comma 1 or 2 comma 4, it looks like it pretty much goes at a 45-degree angle through this graph. So the slope is going to be roughly 2 meters per second squared over 1 kilogram, or roughly 2. And we have these weird units here, acceleration over mass, but we're really just concerned with the numerical value here. Okay, so if we look at the value of the slope and this equation that we're given here, we can actually just take any one of those data points and plug it into this equation up here. So I'll just take the data point where acceleration equals 2 and the mass equals 1. So we get something like this, which gives us a value of g, which is approximately 10 meters per second squared. And of course, we should expect something close to the actual value of g. All right, so part C hopefully was not too difficult, but part D asks us to be a little bit more analytical here. So it says if the mass of the pulley is significant, would the experimental value of g be greater than, less than, or equal to the value calculated in part C? All right, so we need to think about what would happen there. So if the mass of the pulley was significant, how would this affect the motion of the system? So you can imagine, replacing a very lightweight, almost massless pulley with a really heavy pulley. Well, that pulley would be less willing to get rotating, so it would sort of slow the whole system down. So we can say a more massive pulley would result in less acceleration of the system. So if we look at our equation here, it was acceleration is equal to mcg over m total. So if we measure a lower value of AC on the left-hand side of the equation, then we're going to calculate a lower value of g on the right-hand side. All right, so bottom line is we should see the system accelerate more slowly, so we would come up with an experimental value of g that's less than the value we expect. All right, part E says now you have a different group of students who repeats this experiment, but instead of moving the clay from block B to block C, they just remove the amount of clay and set it aside. So that means this variable m total is no longer going to be a constant. All right, but it does tell us that this equation A sub C, acceleration of block C, equals mcg over m total still applies to this new experiment. It's just that m total will no longer be constant. So it says, in order to provide a straight line graph that can be used to determine an experimental value of g, what two quantities should we now graph? All right, so now, since we're not transferring clay to the block C, then mc is going to be a constant, and this will now be a variable. So when we do this experiment, we're basically going to get a table of values where m total will change and the acceleration will change, and we can plot those against one another. Now the question is this going to be a straight line? Well, if we look at this equation, AC and m total do not depend on each other in a linear way. This is actually an inverse relationship, so we're going to get a graph that looks somewhat like this. So in order to get a straight line graph, the way we linearize this is we would plot AC versus 1 over m total, or 1 over AC versus m total. So we need one of these two combinations of variables, or if we multiply either side by some constant, that will also give us a linear relationship. So if we look through the options here, AC versus 1 over m total, this is one of our possibilities, and there's another one. This is, we could plot AC versus the quantity mc over m total. Either of these will give us a straight line graph, just that they will have different slopes. So if you're going to choose one or the other, you would have to say what the slope is going to equal in either case. So in the first case, the slope of these two quantities will just be whatever is left in the equation up above. So that would be mc times g. Here the slope would be equal to just g itself. So you can determine the value of g either way. Either you have to include mc in your calculation of the slope, or you have to include it in your one of the two variables that you're going to plot. All right, so that should finally finish it for the 2019 International Practice Exam. Let me know if you have any other questions. Thank you so much for watching.